you can take this with a grain of salt if you want to, because every teacher says their test is easy, but I think this test is fairly straightforward. There are no tricks in this test. In fact, the workbook problems are more difficult, especially the harder ones, are more difficult than the questions you'll see on this exam. So if you know conversions, you know moles, and you can manipulate the ideal gas law, you will do fine on this test. Okay, there's not a lot of memorization. It's just using the skills you've learned of how to convert and then applying those skills in this test. Okay, not a lot of memorization there. So let me go through some of these questions. You say, Lily Francis, you say, will we be given the conversions between imperial and metric measurements like the graph displays in conversion to imperial reading? So let me tackle that first with, I think this is it. Yeah, this right here. Okay, so this right here will be given to you on every problem in which you need to convert something. Okay? It doesn't mean you have to use this on every problem that you need to convert something, but it will be given to you. So you don't need to memorize any of this. This will all be given to you. Now, a smart student who wants to save time and wants to ease their mind would be smart to look over this and know where things are, vaguely. I mean, know where, like in terms of length, where you can find those kinds of conversions and what kind of conversions are included there. So if you, like for instance, need to change a millimeter into a mile, well, think about how you might do that. Well, you'd go from millimeters maybe into, oh, here's another millimeter conversion. You go from millimeters into feet, and then feet, well, I don't know what you would do. I guess you might go millimeters into kilometers and then go into miles. That would probably be the best way of doing this. Yeah. So just be familiar with this. Be aware of where these things are. This right here is the ideal gas law, and here's the R, the constant for there. The hardest part about the ideal gas law, and this is a small memorization piece, is that the pressure is always in pascals. The volume is always in meters cubed, so you might need to do a conversion there to get the volume into meters cubed. N is the number of moles of whatever molecule or atom you're talking about, and T is temperature in Kelvin. All right, it's in Kelvin. Right, and here's a small alternate form of the gas law when you're changing volume or you're changing pressure, you're changing temperature, and you're getting a new volume or a new pressure or a new temperature. This equation is going to help you with that. It's really when the moles are constant, what happens to this, ideal gas. So it's when you're like compressing something, or when you're expanding something, or when you're heating something, or cooling something. That's when you use. All right, here are all the metric conversions over here. Be familiar with how to convert those. Okay, since I didn't get any questions about conversions, and I think we've kind of covered conversions to death in this unit right now, I'm not going to go through any conversions, but I'm hopeful that you have been experienced enough with those. And please go through the online practice if you haven't done that already. Go through the online practice and just kind of like, practice a little bit just to become kind of like warmed up before you take the test. It really helps to be warmed up and how to arrange those equations and how to arrange a conversion factor so you convert something into something else. Yeah. Okay. So that will be given to you. You can take a screenshot of this right now if you want to, if this makes you happier, or you can just pause this and write it down so you know it will be given to you on the test. But that will be given to you on the test. Okay, I'm going to minimize it now. Next question. Will we need to know about a lot about plasma, supercritical fluid, and degenerate gas? Could you please go over these? No, we will not need to know anything about these, in fact. These are not on the test. I just wanted to give you a little bit of a background on these things so you could know some slightly different exotic states of matter. Not just a simple solid liquid gas, but there's also other states of matter that are kind of cool. So I just want to make sure you knew that a little bit beyond like what a middle schooler might know in terms of phases of matter. Like matter can be in these plasma forms. It can be in a supercritical fluid. It can be in degenerate gas. I'm not going to go over that right now because it's not going to be on the test, and I know you want to use your time efficiently, so I will go over those and say if you're interested, in which you should be, you can Google them, and or you can go back through my text and read through those, see what those things are. And then you say for the last question, could you please go over how to solve ideal gas problems? I will do that. And then later you go P1 V1 over T1 equals P2 V2 over T2. So we're going to go over a couple of those. Yeah, and that's going to be it for our review session. So it's going to be a sort of quick review session. That's okay. I think this should be a pretty straightforward test for you all. And I hope that everyone will score above a 90% on this. I think you should be able to. Okay, so let's go over some ideal gas law problems. To do that, I'm going to pull up a fresh sheet, and I'm going to look at some workbook problems. Okay, here we go. The first workbook problem, I'm going to, whoa, hello. I just looked up, and all of a sudden, we've got a, there we go. Okay. Let's see, let's find one that a lot of people got wrong. I'll do the, what's going on here? I'll do the problem where you squeeze. Yeah, I'll do number 3 in the warm-up problems. I don't know what's going on here, but I'm gonna get another new one. Okay, so I'm going to do number 3 in the warm-up problems in your ideal gas workbook. Okay, so for this one, it says a 1.2 Pascal sample of gas at 245 Kelvin and 2.4 meters cubed is squeezed to 1.9 meters cubed. This raises the pressure to 1.7 pascals. What is the new temperature of the gas? So we're given a lot of information here, and I suggest when you first get any problem, just to write down what you know. And then you can think about what equations you might need to solve, or use to solve this question. So let's look up here. We say some 1.2 Pascal sample of gas at blah, 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 blah. Okay, so we know that the pressure is 1.2 pascals. And that's a good unit. We don't need to convert anything from that unit. We know that the temperature is 245. So we know the temperature is 245 degrees Kelvin. So that's great. We also know that it is got a volume. The volume is 2.4 meters cubed. And we know that that is all we know about the gas, and it says it's squeezed. It's squeezed. That's crucial. Once you see some kind of like verb there where it says condensed or squeezed or lowered, temperature is lowered or raised or whatever. When you do something to a gas, that should give away. So when you do something to this gas, so when you do something to a gas. Can I write this out word for word? When you do something to a gas, you should think that we're going to be using this equation. P1 times V1 over T1 equals P2 times V2 over T2. The 1s and the 2s just mean before you do something and then after you do something to the gas. Okay? So when you're doing something to it, that means that there's something this gas is somehow changed in some way. So the volume's changed, or the pressure's changed, or the temperature's changed. And it turns into something new. So this is the new, and this is the old. This is what we start with, and this is what we end up with. It's actually okay if you really feel like switching those around and saying this is the old and this is the new. It really actually doesn't matter in these equations. But I like to just put, as a matter of my own convention, I like to put what's old over here and what's new over here. So so we know that this is the starting gas. It says we've got this gas and you squeeze it. So I'm going to say that these are the starting. So I'm going to put that little 1 next to all of those. And I'm going to even use a different color for the new gas. So the changed gas, it's squeezed. So the new gas is squeezed to a different volume. So the volume of the new gas, the V2, it says it's 1.9 meters cubed. And these units are awesome. We don't need to convert anything here. Okay, it says this raises the pressure to 1.7 pascals. So the pressure now of this new gas is 1.7 pascals. I'm just writing this out in the same order as this one right here. And I'm guessing it's going to have a temperature too. So it says, what is the new temperature of the gas? Oh, that's what we need to find. We need to find that. So T2 is what we need to find. The new temperature of this gas once it's squeezed to this and that from our starting conditions over here. So this equation is great because it tells you what the gas does, how it behaves. If you have a normal kind of like sealed container and nothing escapes from this container, you can really predictably tell what the temperature is going to be, which is really cool actually. It's like, imagine that, like you have this balloon, and if you squeeze a balloon to a certain volume and a certain pressure, the temperature is going to raise, and you can predict how much that temperature is going to raise, and you'll be right. That's awesome. That's very powerful. That's science. So I'm going to just write over the top of these in green so it's a little bit easier to see that this green corresponds to that green. Okay, right. So in this problem, it asks you to find the new temperature of the gas. So you're going to be finding the new temperature T2. Everything else is given. Now, I highly, highly, highly recommend what you do is you take this whole equation here and you solve for T2 before you do anything else, before you put any numbers in. Believe me, it will save you so many points and so many errors if you do it this way. I've been teaching this stuff for about 8 or 9 years now, and students always get confused when you start plugging in values right now. Don't do that yet. Wait until you solve for T2 all by itself. So when I say solve by T2 all by itself, I mean I want you to isolate T2. I want you to get it on one side of the equation and everything else on the other side of the equation. So I'm going to do that right now. I'm going to use some algebra. The first thing I'm going to do is I'm going to say, okay, well, I want T2 by itself, so I like T2 in the numerator when I want it by itself. I'm going to try to multiply both sides by T2. What that'll do is that'll cancel out this T2 on the bottom, and it'll just multiply it on this side. So I will write out that step right now. So it's P2V2 over T2, and I'm going to multiply this whole side by T2. Okay, and I'll use correct colors. So this is going to be P1V1 over T1. And again, it's multiplied by T2. Both sides are multiplied by T2. So what that does now, look at this. That gets rid of my T2 over on that side. So now I've got T2 over here times, I'll just write out the rest in green that I have in green on this side. I'm just going to rewrite this now so it's not so cluttered. This whole thing, P1 V1 divided by T1. Okay, so now what do I do? Let's see. I want to get T2 by itself. So I can do something really quick. If you know algebra really well, you know what it means to multiply by the inverse fraction of this. So you can do that, but I'm going to do something, I'll just do it step by step. So the next thing I'm going to do is I'm going to multiply both sides by T1. Alright, if I multiply both sides by T1, what am I going to get? I'm going to get, okay, I've got T1 over here, T1 times, I'll put in that T2 in a second, P1, T1 equals, and now this side's going to be multiplied by T1. Now I'll put in the green terms. This will be T2 over here still, and over here it's going to be P2 times B2. Right. Now, what do? Now I multiply, okay, well, now I'm just going to say that this crosses off. These two cancel out because there's in the top, same term at the top and the bottom, and they're all multiplied by each other. So this is going to be T2 times P1, oops, P1 times v1 equals on